I'm here in San Francisco. You got a new startup. It's low power. It's impressive. What do we got here?
Yeah, it's good to have you, man. It's been a while. So let me talk you through the vehicles. So we have a fleet. We have two vehicles, which is technically a fleet. We have one vehicle there, one vehicle here. We use these vehicles as a test bed for our AI because we're building a robot for next year we're launching, and we want to see if the AI works. So it's what we do to validate that. Let me give you a quick tour of what's happening on the vehicles. So, here, someone's camera here, on the side mirror, looking backwards, away from the door. Felipe's in there. We have a camera sitting up under here. Used a hot glue gun to stick that in.
Oh, fancy.
So you can see we're running our UX on the screen. And another camera up here. So that's our side camera.
Wow.
And if we go around to the front, this is compute stack. So we have an NVIDIA Orin AGX here running at about 33 watts. You can see the camera feeds coming in, going through these pucks into the computer. This is actually the aircon from the passenger footwell. We broke that off to put it in here so we keep the computer cool. Don't need it here. And then this computer running 33 watts is going to process the cameras, run the neural network, output instructions to the car through the CAN bus. And we're off to go. You want to go for a drive?
Let's go for a drive.
All right, let's do it.
So, Tim, you showed me the future today. Continual learning. I was impressed what I saw. What's HYPRLABS building?
Hey Grayson, great to be with you, great to be on your pod. And it was exciting to have you in HYPRDrive today. You're actually the first person outside the company that's experienced what we've been building. So super excited to share it with you. What just happened? I mean, you tell me, what was your experience like?
Impressed. I'm really, truly impressed of what you built. And I'll say this, your car, HYPRDrive, was the nice pedestrian car. It was very nice to pedestrians.
Yeah, it's got a good understanding of pedestrians. In fact, the full stack of driving in downtown San Francisco. It's an early stage development. The vehicle you were driving in was our platform test vehicle. We actually have two, so we have a fleet, minimum viable fleet. And we've put our own cameras in there, connected them into an NVIDIA Orin AGX, which is a computer about this big, running at 33 watts. And then we've connected that computer to the car's CAN bus to get telemetry and send actuator signals. And then we also connected it to the in-vehicle screen as well, where it's driving the UX of the screen. And what you saw today was a vehicle running on 33 watts of power, driving through downtown San Francisco using 5 cameras. And the neural inference was running at 12 watts, which is about half the human brain. We use about 20 watts, running about twice the sample rate, 100 milliseconds versus 200 for us. And the exposure time on that vehicle in terms of the amount of driving instruction it had was about 1,600 hours, or at 10 miles per hour in downtown, average, around 16,000 miles. And what's unique about this system is it's only been exposed to data while it's driving. So we don't use any external data sets, any heuristics, any hand coding, any simulation, any HD map, none of that stuff. We actually think that stuff is counterproductive to performance and capability. They actually inject structural noise into the model. And so our AI has learned to drive that vehicle through San Francisco, only being exposed to data created on vehicle as it goes through the environment.
Low power, not a lot of data. How are you pulling it off? What kind of algorithm did you write?
Yeah, so, HYPRLABS is a lab. We've been in stealth mode. We develop artificial intelligence. We develop robots, which will be launching next year, and the product. We're showcasing HYPRDrive now because this is the technology that will be on our product that we're launching next year, because we wanted to see if artificial intelligence could handle driving down the road, and it turns out it could. So getting the car driving was actually just a side mission while we're building our own robot. but it worked quite well.
I'm sorry. It's more than a side mission. You put me in your vehicle and you've got the foundation for something special there.
Yeah, so our philosophy at HYPR is robots learn best when they learn as they move. We think that there's a new phase coming now in robotics and artificial intelligence, where the winners that will win are the ones that create systems that learn interactively in their environment and are enabled to learn continuously. So this requires a different tooling, a different frame set and mindset, and a different framework. And so that's really what we've been building at HYPR is what we call learning velocity. You know, what we're focused on is how fast can you turn exposure into intelligence. And in a world of compounding exponentials across some form of Moore's law, some form of the scaling laws, and some form of the algorithms themselves, helping with their own curation and advancement, that's a triple exponential system that's compounding. That means that learning velocity becomes even more important. And the performance that we've been able to get today, as you experience 12 watts of neural inference driving through San Francisco, you know, the system isn't perfect, but as you saw, it's making really smart trade-offs in really complicated situations and doing all the basics of driving. We think is a proof point that the way we're approaching robotics and artificial intelligence has great efficacy.
We went through some complicated scenarios, unprotected left-hand turns, people walking across the street where they weren't supposed to, bicycles. We saw all sorts of interesting things. How do you teach robots to learn in their environment? Because downtown San Francisco is not exactly the most ideal playground to play on.
Right, so it's a complex environment. You know, broadly, when you're talking about artificial intelligence, robotics, moving through what we call the fundamental domain, the real world environment, they need to learn the policy framework for the environment. They need to learn the dynamics framework, how they move and also how agents move around them. And they need to learn the behavior framework, right? There's the policy of what the rules are, but people don't always follow the rules. And I think what our insight is that you're best to learn those three variables in one unified latent space in an end-to-end neural network. And you're best to learn it fundamentally from data that is happening on vehicle. We call it at runtime in situ as the robot or the vehicle moves through the environment. Because then it's modeling the correlations and understanding the causations from the fundamental domain. If you do it in the simulator, for example, which a lot of people do, in fact, we don't know anyone that's doing robotics and autonomous driving with zero simulation, classical simulation, there's a gap between the simulator and reality. And to us, that gap actually means you're injecting structural noise into the model that's actually suboptimal. And if you take the leap just to let the model do what it's best at, then you're going to do very well.
The noise comes up a lot as we see with the sensor arrays. How much do you think noise slows down the development acceleration of autonomous driving?
Massively. You know, if you're running complex pipelines, module-based pipelines, engineering teams in the thousands, complex sensor arrays, kilowatts of compute, in my view, you're not going to make it. The performance you saw today was created by 4 engineers, 3 algorithmic architects and 1 infrastructure engineer. 4 people. We've been working on that vehicle for about a year and a half. We were working on little remote controlled cars on the sidewalk before that. We got them working pretty well. So we said, could it work with a full scale car on a full built road? So we decided to do the side mission, as I said, and we actually got it working pretty well based on the principles that we went through.
I need to clarify for my own sanity and for the audience. You said 1, 2, 3, 4, not 40, not 400. I heard you right. Was that right? 4?
Yeah, that's right. They're very good.
What's the secret sauce? Do you have a robot working in the lab with you that we don't know about?
We do, more than one, but they're coming out next year, not this year. I think the secret sauce is clarity of vision and also a deep understanding of the medium that we're working with. You know, I think historically there's been a brute force approach to AI. It's kind of like a toddler with a hammer going in super hard. I think we're transitioning now to a moment where teams that actually have been touching this technology for years in the field and understand it deeply, you're going to see huge performance coming from very small teams. Because you really need people to understand how to architect this and then get out of the way and let the model do its work. And this is kind of counterintuitive for most engineers and most safety engineers. They want to decompose a system in a way that's interpretable to them. And we take the opposite view, where like every time you do that, you're actually hurting performance and hurting the model. You know, to give you an example, in traditional robotics, you start by defining the object. You might do supervised learning or training that does a box detector that says, hey, this is a car and this is a bicycle. You're starting at the object level. And then you have a planner and a prediction module that, given that class, makes predictions about the environment. Problem is, you're driving your robot down the road and all of a sudden you see a bike on the back of a car. And so your prediction model's wrong. It's now slamming the brakes. It's like I'm about to hit a cyclist. So then you do a JIRA ticket and your engineering team goes, okay, we need a new classifier, a new object ID that says a bike on the back of a car on the road is actually okay. And this becomes a spiral that becomes unsolvable. We think the right thing to do is to do the exact opposite. Don't start with the object class. Let the AI model the environment as it's exposed to it and let it make the correlations in the data. And what it's doing is it's understanding the relationships between the data, between the objects. In fact, our vehicle, it doesn't know what a car is. It doesn't know what a traffic light is. It doesn't know what a pedestrian is. We haven't told it any of that. It's domain general. I mean, you could put it on any vehicle and it's going to learn. It has nothing to do with being on a car in San Francisco. The point is that we're allowing it in its latent space to model vehicle dynamics, behavior, policy. Now, that's hard to interpret traditionally in terms of engineering, but in terms of performance, as you've seen, it's phenomenal. 1,600 hours of exposure time, 12 watts of neural inference, and we're moving a 4,000-pound vehicle through downtown San Francisco pretty well.
What happens when you hit 5,000 hours, 10,000 hours, 20,000 hours? Is it performance increases, or what gets unlocked?
Yeah, so one of the beautiful things about working with this technology is we've been developing this for a year and a half in terms of a road platform vehicle. I mean, initially we struggled just to stay in the lane for months, right? And then as we tuned the system, we understood it. We built our own frameworks, our own feedback loops, which are novel. You see more complex behavior emerge. You know, we weren't seeing pedestrians 3 months ago. Now it's seeing them, as you saw, really well. It's able to have right-of-way through an intersection, wait for the pedestrians, and then go through the intersection. And all that's learned from the data. And what we saw is about the same time as it figured out what a pedestrian is, it also figured out four-way giveaways, right? And so you see this emergent behavior. Now, I think the performance we're getting with just 16,000 hours of exposure is very good. What does it take to get to a production-grade system? That's a bigger question. But fundamentally, what we've actually tooled here is a system designed for scale. You know, traditionally, you can't do, you need a simulator because you can't get the iteration up with real-world robotics. That's about to change because we're about to have fleets of robots in the hundreds, the thousands, and the tens of thousands. And so that means that the fleets can actually do enough miles, enough sampling of the environment, that they can acquire enough data and then validate themselves in the environment as successful. So to be clear, we think it is going to take more data. Our rough estimate, we don't know exactly, but our rough estimate is around 2 orders of magnitude, so maybe 100,000 hours of training data, which at 10 to 20 miles per hour, average speed in a downtown city is in the order of 1 to 2 million miles. But that's relatively small amount of miles in terms of totality, but we think that's probably enough to get the system working really well, because it's not really about the 2 million miles. A lot of those miles after a few thousand are actually going to be redundant. It's about exposing the system to the variance that happens so you can capture those moments, train on them, and become robust with them.
Then as you add more miles, more data, how do you eliminate the noise?
Well, we've eliminated the noise by the way the system is set up. As I said, we optimize for learning velocity, and we've optimized for continual learning. So to give you some insight into the pipeline we've created, initially we put the sensors and the compute into the vehicle. That's all we do. We don't even calibrate the cameras. We don't even use any ground truthing. So some people have vehicles with LiDAR on them. They go out and ground truth distances and use that for the model. We haven't even done that. We have injected nothing exterior to the vehicle into this model and how it learns. So the first thing we do is we have a coach, we have a driver in the vehicle, drive the vehicle, and we pair what they do with the actuators, the action, with what they're seeing, the sensors. We then train the model on that, and it builds an understanding of the relationships. Once it's at a level that's reasonably proficient, we then put the AI back into the vehicle. We now have it drive, but we do something a little bit different that we haven't seen people do. We've created what we call hybrid mode, which means as the AI drives, if the instructor thinks it does something that's suboptimal, maybe it doesn't take quite the right curve through an intersection, without disengaging the AI, in real time, they can override with the steering wheel and give the correction. What this does is give the model the exact high-value bit it needs that's missing. Because that high-value bit is sparse, they're happening at a low rate of incidence, even now at 1,600 hours of data. It's small enough that we log that, we call it guidance feedback. We log that to the disk in the vehicle, H.264 video. We then encode that video into the latent space that the neural network uses, which is around a 10-to-1 compression over H.264. And then because that is sparse enough and low data enough, we can then stream it from the vehicle over its cellular network to our cloud. Now, most people can't do this because they're running too many sensors and they're logging too much data. They have to drive to a depot and use high bandwidth Wi-Fi or pull hard disks out and do it manually. We've built a system that actually does it from the fleet level to the cloud. So we have a minimum viable fleet of 2 vehicles. You can imagine when you had a fleet of 1,000 vehicles or robots, they are streaming these corrections in real time. In the cloud, when we have sufficient feedback of an epoch, we then train the model. We run regression tests on the model in the cloud to make sure it's improved performance. And then we don't even send the full model back to the fleet because we're obsessed about learning velocity and hyper-efficient systems at HYPRLABS. We just send back the delta change in weights in the model. So just what changed in terms of the weights, which is probably around 10% of the total model. We stream that back to the vehicle and then continue to drive to validate it. So this whole system that we've created runs in real time, is continual learning, and the system self-actualizes as we go. The other interesting part that we do is as the AI gets better, you can use it to improve itself, which is the self-actuating part. So for example, if the vehicle is driving through the environment, as it compresses the sensor data into its latent space, for almost no computational overhead, it can make a density estimation of whether the environment it is in is novel or not. If it's a novel environment, we do the same thing, log it to disk, send it to the cloud. So already we don't record all the data, we just record what's valuable, which creates an incredibly efficient flywheel.
And efficiency is clearly what you're developing here. And when you open the frunk and you showed me how small the compute was and everything, let's take a step backwards. What are the origins of this approach?
Yeah, it's a great question. I think for me, it was looking at some of the work that was happening with Google DeepMind through sort of 2015 to 2020. They released an algorithm called AlphaGo that with the rules of the game and heuristics of how humans play it, became superhuman. They didn't stop there. After this, they then released AlphaZero, and the zero meaning zero heuristics. So we only give you the rules of the game. We don't give any prior game histories. And they generalized that to chess. And that became the strongest chess player in the world at the time. But they didn't stop there. They went to mu zero. Mu means model, so model zero. And this time, they didn't give the rules of the game, and they didn't give any heuristics, any game history. And for sort of an equivalent amount of compute as AlphaZero, it got a comparable ELO, or rating in chess. But here's the interesting part, right? I mean, most people stop at like, without knowing the rules of the game, just iteration and inferring them, and with no game history, it got as strong as AlphaZero. But the interesting thing is that AlphaZero took about 4 TPUs to run, right? Custom ASICs. Mu0 run on 1 GPU. And so the lesson is, or the insight is, that with less interference from humanity, don't give it the rules of the game. Don't give it examples of game history. Not only does it get to superhuman performance, it does it in a more efficient computational way. And that's really what we've built at HYPRLABS. We've got out of the way of the algorithm to let it model the correlations. And I think what we've proved to you today is something quite stunning, which is incredible performance given the amount of data, given the size of the team, and given the amount of watts it's drawing out.
The inspiration by DeepMind is beautiful, I'll say. But where did the trust come from with you to say, hey, I'm going to build this company and I'm going to let the brain be a brain and teach itself?
Well, it's a lot of fun, isn't it? You know, and I think creating beautiful, elegant, scalable systems that are intelligent and energy efficient and safe and can contribute is valuable work. So that's why we do what we do.
It's valuable work, but there's trust. You have to trust it.
I mean, I think that's a great point, is building trust. You know, remember when you were a kid, I've got a toddler. You don't start on a bicycle, you start on a tricycle. 3 wheels for stability. And I remember being a little kid on 3 bikes, and you look at those kids on 2 wheels and you're like, well, that's crazy. That's never going to work. Right? Because you don't have trust. You're used to 3 wheels. And eventually you make that transition to 2 wheels, but you have training wheels. But at a certain point you realize, you know what, these training wheels are actually hurting my performance. I need to get rid of them. And I need to let myself move with centrifugal force, with the geometry of the steering of the bike that catches itself as it falls. All these things are actually non-obvious when you look at the bike that actually make it self-stable. And I think that's a great analog for what's happening in robotics and AI. People think you need LiDAR camera and radar. They think you need modules. You actually don't, in my opinion. Those things are actually hurting performance, making the system complicated, injecting structural noise. Get out of the way. Build a pipeline that lets it learn, and then you might build some trust as you actually see how the system performs.
If you look at that, you forgot the phase, the bad back dad phase, when you have a pole trying to teach the child not how to fall over when you remove the steering wheel. Sorry, the training wheels. Is that where we are today? The bad back phase for dad. And where you're going with HYPRLABS, is that the no training wheels, no bad back for dad phase?
Well, in some ways, the safety driver or the instructor or the coach, whatever term you want to use, they're performing that role, right? And so the safety driver will intervene to stop the vehicle having an accident while it's learning. And, I think another thing that HYPRLABS has done is a little bit counterintuitive, as most people have had the opinion, well, look at reinforcement learning. The iteration is too high. Iteration rate is far too high. We need to go into simulation. We can't do it with real-world robotics. And we thought differently. We thought actually you can do it. You need to figure out some of the techniques of how to do it, which we've talked about, and you can actually get through to really good performance.
Why do you think, if I'll use the term mystique around simulation, why is that still brewing when what you've showed me clearly demonstrated you can make a car drive itself without simulation?
Well, people are entitled to their opinions. I'm entitled to my conjecture, and I'm entitled to make predictions from that and go out and validate it and show that it works.
I have a lot of opinions, as you know, and what I saw today and experienced, it worked.
Cheers, man. Thank you. Thanks for being the guinea pig.
I love being the guinea pig. Please sign me up anytime.
Yeah, we'll get you back in 6 months and show you the progress. Let's do it.
It's done. It's here on the record. I'm recording this on December 14th. It's on the record. I'm coming back in 6 months. I'll see you in June. Is this the phase potentially where everything was pre-mapped, and then we went to mapless. Are we at a similar stage there, potentially with simulation?
I mean, when I say simulation, I do mean classical simulation. Sort of building a model of the world in Unreal Engine with engineers and, very computationally intense, large teams fighting every day to close that sim to real gap. We think that's not the way to go. There is a thing called neural simulation where the world model, the AI's own understanding of the world, you can actually use that to create an environment. And I think that's going to be important in the future. At the moment, it's the latest carrot to dangle in front of an investor to get some money. It's not performant, but it will be performant. And it's going to be valuable in the validation phase. But that neural simulator needs to be calibrated to real world scenarios so that you can trust it, just like you have to do with a virtual simulator, right? A classical simulator. So that's some of the stuff that's coming down the pipeline in terms of thinking about, okay, we have this system, it's a neural network-based system, how do we validate it? Some of those tools will be valuable in the future on the neural level.
Prediction, when do you see that potentially scaling and coming across all of autonomy?
By definition, a Brownian system is hard to model, even if you're a neural network.
Okay, I'll take that. That's fair.
So there are some phenomena, because the input space is unknown, that it's almost impossible to predict. And the financial market is an example of that. There's too many actors pulling too many strings. Whereas driving a vehicle through a city or a robot through a street or any sort of built environment is a more predictable environment. So that's doable.
What happens when you take your system to a non-San Francisco location? Let's say you're going down to Palo Alto or you go down to Los Angeles. How is your system going to adapt to those environments?
Yeah, I mean, we have a fleet of 2 vehicles driving 10 hours a day, 7 days a week. So we're not logging a lot of miles. If you had a fleet of 1,000 or 500 vehicles, you could crush that straight away. So you could actually train the model from scratch in the new environment. By the way, to train our model from scratch in the cloud cost us $850 for the model that you saw today, because of all the hyper efficiencies we put into the entire pipeline. But what you would do to answer your question is you would have a foundational model as we've built. You would go to your new environment and you would validate it in that environment and fine tune it into any sort of novelty that's in that system. Maybe different traffic lights, different language sets, etc., etc. So it will learn faster if it has a good foundational model, but you can also just create it from scratch as well if you have the right fleet size.
$850. How many thousands of dollars of cloud credits do you have on top of that?
I don't think we have any. I think we just pay for what we use.
How did you do that?
Do what?
How did you train your model for $850?
Well, it's just a function of the size of the data set and the amount of computation it takes to train. I think roughly 120 H100s in an hour from scratch for $850 and probably about $20 of electricity could train the model. Obviously, once we have it trained and it's running in the fleet of 2, and we're doing corrections to the cloud and we're fine-tuning, I mean, that's an incidental amount of capital.
So what you're describing could fundamentally change autonomous driving forever.
Well, I want to be clear that we're not saying this is a production-ready system. It's a system showing great promise, and it's designed for scale, for validation. So in the case of, say, a robotaxi, and I want to be clear, we're not saying HYPRLABS is going into the robotaxi space. We're actually building this technology to put in our own robots, which is not a robotaxi. It's a new category we're launching next year. However, if people want to chat to us about it, we're happy to have some conversations. I think one way to think about it is that, let's say you have a fleet of 1,000 robotaxis in the Bay Area. They're doing 16 hours a day, 16 miles per hour average speed. That's around 250 miles per day times 1,000. So you're actually doing 250,000 miles per day. It's a lot. That means in a week, you're probably going to do over 1 million miles. That's statistically significant. And so with a fleet of 100, 500, or 1,000, with the HYPRDrive pipeline that we have, which is optimized for learning velocity, you would quickly accrue exposure to the data you need, train on that data, and then you use the fleet itself to validate the safety of the system. Now, sometimes safety is proved by removal of unreasonable risk using simulators. using lookup tables, right? Because they've actually done it. What I'm suggesting here is using what's called proven in use. You know you're safe because there's a performance target and you went into the environment with the vehicle and hit that performance target. And that's actually the gold standard because you did it. And so what I'm suggesting is there's a virtuous cycle where you can acquire the data, train the model, and validate it in probably weeks to months. As you go through seasonality, you're going to have to make some adjustments. But compared to any other framework, look, if you would tell a tier one, I need a radar on my vehicle, it's going to cost a lot of money and it's going to take a lot of time. So this can happen very quickly. And that's what I was saying to you is we think the game is shifting in robotics beyond conversations around end-to-end. It's really around learning velocity. How fast can you turn exposure into intelligence? Those are the people that will win.
Exposure to intelligence is fascinating, and you're building a new class of robots. What are those robots learning from the data that your system is gathering on the roads? Is it all compatible and transferable?
That's a broad question. Obviously, if it's exposed to a road environment driving through it, and then you put it, in a kitchen at a house, it's not going to do particularly well because it's quite an alien experience. There is a world where you can create foundational models that understand all these topologies, and over time, that's ultimately what will happen. But I think what we're showing here is that within particular verticals, you can get very good performance by the way you let the network model the environment, the fundamental domain that it's interacting with.
So how will that change when you put your robots in a non-automotive, non-road environment?
Well, I think it's quite valuable technology because if you can run very low power, very high performance with quickly acquired compact data sets, you really have a distinctive capability. The robot we're building for next year, we're pretty confident people cannot touch in terms of its performance metrics without technology like HYPRDrive. The robot next year we're going to operate runs on one camera. Comparable people are running many cameras and other sensors like radar and LiDAR, et cetera, et cetera.
One camera. What I experienced today was low power. Is your overarching goal efficiency?
Our overarching goal is kicking ass.
I'd hope so with your track record, yes.
Well, we'll give it a go.
It just seems that I know I'm picking at this here because I'm curious that you're unlocking something that really hasn't been commercialized before.
Well, robots are being commercialized. We're at an inflection point now where there's a lot of buzz because people are like, maybe this is the moment where robots with AI can come into the general population and do general work out of the factories. It's well commented on. I agree with that sentiment. I think we're close. I think we're going to start seeing over the next 2 to 3 years shift in that direction that's real and meaningful. The game is going to change to, again, how quickly you can do it and at what price point.
We saw how quickly you're making the car drive itself, and the amount of money you spent is impressive. And I want to highlight for the audience here, we were in a Tesla Model 3 and we're going to release the video. It did not use the autopilot system. You had your own cameras, your own compute. How did you place the cameras? How did you determine where to put them in the vehicle?
Well, to be fair, we tried to use the autopilot cameras, but they're all encrypted. And so without a handshake from the autopilot camera, they don't like to wake up. So we put our own cameras in. That's really just a first principles question. The robot obviously needs to see what's happening, and so you need to put the cameras with the right field of views in the right locations to enable that. And so in our case, we had one forward camera. As you saw, we had 2 cameras on the interior B pillar just looking through the glass of the side windows. And then we had 2 cameras looking backwards stuck under the rear view mirrors. And that's actually enough to drive through the city.
I mean, how many cameras do you think you could eventually shrink to make a car drive itself?
I think 5 to 6.
Where would you put those 5 to 6 cameras?
Well, I just went through that. I think having one on the face shield down low is critical because you see everything as you come out of occluded situations like garages with sidewalks. You also see under vehicles. If there is an issue with the sunlight, for example, that camera can actually really help you because it's so wide. The sun is small and you can still see in front of you what's happening, and you can leverage the megapixels of that camera to essentially have 2 for 1. You can crop in at a higher resolution to a more tight area and rectify it, and then you're in great shape. You know, we do that, for example, on the forward camera. We have 1, most people have 3, but we've turned it into 2 by cropping in at a higher resolution to look at traffic lights further down the road. I don't know why more people don't do it. It works really well.
Experienced it. So you've made a car drive itself. You're building a new class of robots that you'll introduce next year. What's coming after that?
A lot, man. Stay tuned. You know, we've been cooking, and we have some really, really crazy stuff coming out, and we're going to be excited to share it. You know, I think what's going to be interesting about HYPRLABS is we don't do biomimicry, humanoid, robodog. You know, I like to look deeply at the terrain you're trying to solve for, and then come up with a novel architecture that's optimized for that task. Now, that's a much harder road to take, because you have to, there's no reference for what you're building. But if you can pull it off, you then have a competitive advantage that other people don't have. And it's more fun.
So as we're accruing more data, we're also compactifying it down at the same time to create a faster flywheel. So this is really nice. Orange got orange flying it.
Cruising through here, no problem. And that was the drive. What do you think?
This is great. Well done, sir.
My pleasure. Well done, HYPRDrive.
Well done, Hyper. You got to stay tuned to what Tim and the team are building at Hyper. Somebody tells me something big's coming. I don't know what it is, but something big's coming.
You're the first person in the vehicle outside the company, and it's been an absolute privilege and pleasure to have you today, Grayson. So thanks for coming over.
Thanks for having me. This was great.
Cheers.
The future's bright. The future's autonomous. The future is Hyper.